Yesterday we did an activity where we illustrated one of the two qualitative implications of impulse. The first one occurs when we have an object that is stopping. An object that is stopping will always experience what I call a predetermined impulse. That car is traveling down the road at 10 meters per second. Its mass is 1,000 kilograms. Its momentum is 10,000 kilograms meters per second. One thing is for certain. Its momentum right now is, two things are for certain. Right now, its momentum is 10,000. Its momentum will, at some point in the future, be zero. If its momentum is 10,000 and it will be zero, its impulse is going to be negative 10,000. Agree? It doesn't matter how that car stops, whether it comes to a gradual stop at a stoplight or whether it hits the concrete wall, its impulse will be negative 10,000. Impulse does not hurt you. You're on an airplane that is massive and traveling at 800 or 900 kilometers per hour. The impulse experienced by the airplane is huge, but you don't get hurt when the airplane stops because it's not impulse that hurts you. The impulse in both of those cases, in all cases where an object is stopping, is predetermined. That predetermined impulse is equal to F times delta t. Now, we said yesterday that that impulse doesn't go up or down, it's predetermined. But what does change is the time and the force. If I can somehow take longer to stop, increase the stopping time, then I will, in conjunction with that, decrease the value of the force. It's force that hurts, not impulse. So you can have a gigantic impulse. As long as you can spread that impulse over a long period of time, you can reduce the force. Make the force a manageable amount so that you don't get injured. I'm going to write a little note above this here. In this scenario, when we have a predetermined impulse, when we're stopping an object, we say that F and T affect each other. In other words, as time goes up, force goes down. As time goes down, force goes up. F and T affect each other. They do not affect delta P. Delta P is a fixed value. It's going to be the same no matter how the object comes to a stop. The only two variables here that will change are force and time. As one goes up, the other goes down. This is the basic principle behind anything that cushions an impact. We said this yesterday, right? We did an activity on this with our egg drop yesterday. When we cushion an impact, the goal is to increase the stopping time to decrease the force. Now, there is also one other principle at play sometimes in something that cushions an impact. You're wearing a hockey helmet. There's some foam inside that hockey helmet, right? And that foam will increase the stopping time of your head, which decreases the force on your head. That's important. But the hockey helmet will also, and this is kind of aside from this, the hockey helmet will also take that force and spread it out over a bigger area, over your entire head, as opposed to just one localized area. So it kind of works on two things. This and the whole idea of spreading out that force over a bigger area. Goalie pads. When I was a little kid, I remember my friend across the street was we're playing hockey out on this little rink that was in my parents' side yard, and he's taking shots on me. I'm playing goalie. I don't have a helmet on, but I've got a hockey glove on and a baseball glove, and I've got shin pads, like regular hockey shin pads on. And he's taking these shots on me, and I'm doing pretty good. So I say, take a slap shot. So he takes a slap shot, and I go down like this to stop the puck, and the part of the shin pad that covers the knee kind of opens up. And the slap shot, the puck hits me literally right in the kneecap. It hurt more than you could believe, more than you could believe. Okay, but yet goalies, like real goalies, get hit with slap shots much harder than my friend across the street took. So how does it not hurt them? Well, the goalie pads increase the stopping time of the puck and decrease the force. But the goalie pads also increase the area that the force is spread, right? So it decreases the impact on you in two ways. Decreases the value of the force and spreads the value of that force out. Okay, the other situation is where we have a non-predetermined impulse. This is when we're starting an object. This is the golf ball or even a baseball that's moving towards you. Swing the bat, hit the ball. You can start it from rest or you can start it moving in another direction. In any case, you have a non-predetermined impulse. You're changing the impulse here. You're affecting the impulse here. It's still represented by the equation, delta P is equal to F times delta T. But this time, changing the force does affect the impulse. And changing the time also affects the impulse. Here we would say F and T affect the impulse, not each other. So it's kind of opposite, right? In the top case, the top scenario, we have F and T affecting each other, not the impulse. In the bottom scenario, we have F and T affecting the impulse, not each other. Got a few questions for you to work on for homework tonight. No new material today, just a review of the last couple of days and checking over some work. The questions that I want you to work on tonight are not 1 to 13. I'm going to take it easy on you a little bit. We're going to make it page 467, number 4, 5, and 6, and 11 and 12. So we've got, 5 questions, plus, remember your practice questions. Practice question number 3. And I think there was 3 questions on there. So you got a total of 8 questions to do tonight, in addition to your quiz tomorrow. Remember what we've always said, guys, and we'll continue to say this through the year. Regular homework, even though you got 2 things to do here, 4, 5, 6, 11, 12, and the practice questions on Google Classroom, it shouldn't take you more than a half an hour, right? If you're taking dramatically more than a half an hour, you should pause and come and see me and ask me questions about it.